Hello everyone. Today I'm going to give you the video solution to the first year college problem that Professor Walter Lewin has recently given 2 days back. And so here goes the solution. So the question states that there is a composite system of two blocks of mass m and 2m. I've considered 2m equal to capital M to generalize it a little bit, connected to two identical springs, each of spring constant k, in their natural lengths initially. There is no friction between the floor and the block of mass capital M, but friction does exist between the two blocks and the coefficient of friction is mu. The question: by what maximum distance can the system be shifted so that both the blocks execute simple harmonic motion together? That is, there is no slipping between the two surfaces of capital M and small m. Now let us shift the system by x to the right. So we have shifted it to the by x to the right, and now just after the instant we have shifted, let us leave it, and so it will have an acceleration of a to the left. Now, how I'm going to proceed with the solution is pretty simple. I'll identify a system, the forces on it, and write F equals ma. So first let's consider the small mass m, and I'll do this in the frame of reference of capital M. So what I'm going to do is shift my frame of reference to a non-inertial frame. What happens in this non-inertial frame is that I'll also have to consider the pseudo force on small m. So let's draw the free body diagram of small m in FR of capital M. So there is a spring force Kx acting to the left. There is a pseudo force Ma acting to the right. And because the tendency of motion of small m with respect to capital M is towards left, hence friction will act towards the right. Now let's think about this. Will small m have any acceleration with respect to capital M as long as there is no slipping? Well, the answer is no. And the reason is pretty simple. You can think about it in this way. Get into the frame of reference of capital M and think if there will be any displacement of small m along the x direction. Well, with respect to capital M, there will be no displacement of small m, which means that in the x direction there is no component of acceleration. Hence, we can say that it's an equilibrium with respect to capital M. So I've directly equated the forces Kx equal to F plus Ma, vectorially of course. Now let's consider capital M. Now I'm going to consider this in the frame of reference of the floor. So let's consider this. In the frame of reference of floor, anyhow, the capital mass M will have an acceleration of a to the left. Now there will be a spring force of Kx because of the spring on the left hand side, which will be pulling it, and because for the system capital M plus small m, friction is an internal force, therefore the magnitude of friction should be the same and it should be opposite in direction on capital M as it was for the mass small m. So if for the mass small m, friction was of magnitude f, small f, acting to the right, for the mass capital M, it should be acting to the left and it should have the same magnitude. Hence, they cancel out, being internal forces for the system capital M plus small m. Now we can easily write F equals ma for this system, which means kx plus f equals capital Ma. So now we have two equations and two unknowns, which is x and a. I guess we can solve them easily. So solving this from 1 and 2, we have a equals 2f by capital M minus small m. Now, when friction reaches its maximum limit, which is mu times small m times g, because that is the normal reaction offered between the surface in contact. So when the friction reaches its maximum value, which is F max, which is also mu mg, acceleration will also reach its maximum value. Now, acceleration max is equal to 2 times F max divided by m minus m, which is 2 mu mg by m minus m. As acceleration tends to acceleration maximum and friction tends to friction maximum, x will tend to x maximum. This is nothing but the maximum amount by which we can displace the system to prevent slipping, or there's no that is to prevent so that we can have the complete system to oscillate as a whole. So from equation 1 we have this kx max is equal to f max plus ma max, which is nothing but this, and upon solving we get x max equals mu mg by k times capital M plus m divided by capital M minus m. Now according to the question, capital M was equal to 2m, 2 times small m. So substituting the value up there, we get the maximum displacement to be equal to 3 mu mg by k. So that's the solution to the question asked by Professor Walter Lewin 2 days ago. Thank you and have a great day ahead. Don't forget to subscribe, like and share.